All right, changing gears, tired of derivatives. We just kind of tackled this problem. What was the instantaneous rate of change of the function? Turns out, found the slope of the tangent. We could see how quickly a function is moving up or down. We can do a lot of stuff with derivatives. Differential calculus was what we tackled in the first 5 units. Check. Done. Now we're going to shift into a second major problem. It's really out of 3 problems. AB calculus really focuses on the 2. We focus in on a third and some extra stuff. The second problem that we're going to talk about is if I want to find the exact area under this curve between these 2 points, what is this area? This is when we introduce integral calculus. All right. All right. Well, give you 2 situations. I give you a straight line and I give you a curve. By looking at these different functions, can you find the area under the function and above the x-axis between 0 and 8? And if you look at the one on the left, you should say, oh yeah, sure, I took geometry. This is a triangle. I have formulas for areas of certain objects. So here, if you have a straight line, this question does not seem that bad. This is like an easy question. Use geometry. Just have an area formula. 1/2 base times height. Base is 8. Height is 6. 24. Okay, done. But the second curve, that seems a lot harder, right? Because I was never given an area formula in geometry for a curve that looks exactly like this. The best thing I could do is use like circles, I guess, for those curves. But that's probably going to be tough to do because I'm looking for all of this area here. So this is why, we need to investigate this situation a little bit further. Okay, I don't know a formula for the area formula under this curve. Really, the best I can do is approximate the area. And I can approximate the area using shapes that I do know the area formulas for. And this is right now. Using shapes. I know the formulas. Okay, so let's see. I can decide to maybe use a triangle from there to there. Maybe I'll use a rectangle here. Maybe I'll use another big triangle here. I guess it's a triangle on top of a rectangle. And then I'll use a rectangle here. And if I looked at the area of this first object and this second object and this third object and this fourth object and added them together, I could say my area is approximately the sum of all of those different areas. All right. Well, what I just did was a very arbitrary process. I just kind of threw some objects down willy-nilly, decided to use triangles, rectangles, triangles on top of rectangles. It's not very formulaic. And if I gave you different curves, it'd probably take you a while to figure out the best objects to use where. It's not going to be very efficient. So let's use an efficient process to approximate this area, okay? We are not going to be able to find the exact area under this curve until 2 days from now, okay? We're going to understand the idea behind finding the exact area. We're going to understand how we can find exact areas of straight lines. Okay, but getting this actual answer, this is going to take some time. Okay, so understand that. Answering this question is not going to be done until 2 more class periods. Okay, best we're going to do is approximate it. So we're going to focus a lot of time today on approximating it. Okay, so geometry, using shapes. And the formulaic process to approximate it was developed by a guy called Bernard Riemann. And he created a Riemann sum. The Riemann sum is a formulaic way to approximate the area under a curve. Using specific objects over specific intervals. Okay, Riemann said, well, let's figure out what type of shape we're going to use. Okay, so he says, let's use typically rectangles. So first, understand your shape. We got to understand the height of our shape. We got to understand how many shapes we are using and the width of each of our shapes. And we want the widths to be as consistent as possible. In the previous example, I just kind of randomly threw down some widths of some objects. Riemann says, let's make these widths consistent, as equal as we can. And the width of the geometric figure is called a partition or a subinterval. And you get the width by using this formula, b minus a over n. What is b minus a over n? Well, b and a are just where you're starting and ending. Start and end. And n is the amount of objects you use. So if I have this total distance and I want to split it into 4 subintervals, I would find b minus a over n and understand this distance, and it would be all equal. You know, this would all be equal distances, okay? N being the number of shapes that we have, number of objects we are using, okay? And there are 4 types. There's a left, a right, a midpoint, and a trapezoid. And 3 of them, left, right, and midpoint, use rectangles. We know areas of rectangles just based on sight. And then the other one we are going to use is a trapezoid. We'll talk about trapezoids in a while. We'll talk about the area formula for a trapezoid in a little bit. Okay? So based on sight is really all we're going to be dealing with for a left, right, and midpoint. Let's start with a left Riemann sum. Okay? Again, left Riemann sum is going to use rectangles. Okay, so we're going to use rectangles. We are going to formulaically place rectangles on top of this curve, and we're going to add up all the areas of the rectangles, and that will be the approximation. Okay? Now, the key to this left Riemann sum is the height of the rectangle. Let me show you that in a second. Step 1 is always to worry about the width. Okay, so we are trying to approximate the area under this function from 0 to 8 using a left Riemann sum with 4 subintervals. This is the first thing you should be focused on. 4 subintervals meaning I'm using 4 objects or 4 rectangles. So I'm going to place 4 rectangles down to approximate this area of the curve. Now, what's the width of each of these rectangles if I'm going from 0 to 8? 2, right? That's easy enough to do. Well, that comes from your formula, even though you guys just figured it out by yourselves. The width of the subinterval, b minus a over n, that's 8 minus 0 over 4, that's 2. And we call this width a delta x. Okay, so if you want to go back up here, say this is b minus a over n, that's equal to the change in x, the width of our guy. Okay? All right, so I'm starting at 0, going to 8. The width is 2. I can actually go ahead and plop down the bases of my rectangles. I'm going to go from 0 to 2, 2 to 4, 4 to 6, and 6 to 8. Okay, and this is my first rectangle, my second rectangle, my third, my fourth, right? There's my 4. right? I don't want you to focus on those numbers 1, 2, and 3, and 4. I'm just going to write them down so that you know first, second, third, fourth rectangle. Okay, now we laid down our bases. We need a formulaic height, not just a random height that we decide to use. A left Riemann sum, we are using a specific height. The height is going to be determined by the function value on the left of the subinterval. Let me show you what that looks like. Let's look at rectangle number 2. I will go to the base of rectangle number 2, and I'm going to go all the way to the left of that interval, that base. And I'm going to go to the function value above that leftmost point. This function value will be the height of my second rectangle. So I'm going to use that height. Now, it just so happens that that was the largest function value on my interval. But let's look at rectangle number 4. Point to the height that you would use for rectangle number 4. This one. Okay? I'm not going to go up here. I'm not going to go here. I'm going to use this height for this rectangle over 4. Okay? You guys draw your other 2 rectangles. Okay? We formulaically plot down these 1, 2, 3, 4 rectangles. By adding the areas of these rectangles, which we know the area formulas of, we will have an approximation for the area under the curve. We're going to say the area using a left Riemann sum with 4 subintervals, I'll call them subintervals, subint, is approximately, it's a bunch of base times heights. Now, I'm going to show you how you can use this table of values quickly to write down kind of what your heights are and your bases that you're going to be using. Go ahead and lay down the bases on top of your table as well. 0 to 2, 2 to 4, 4 to 6, 6 to 8. And you can actually circle the function value over the leftmost height in each one. 1, 2 to 4, I'm using 5. 4 to 6, I'm going to use 4. 6 to 8, I'm using 7. So my first rectangle, it's got a height of 1, base of 2. 1 times 2. Second rectangle, height of 5, base of 2. Third rectangle, height of 4, base of 2. Fourth rectangle, height of 7, base of 2. Now, it's actually easy since these 2's are all consistent, which Riemann loves. We are going to be able to factor out that consistent base and just add up the sum of my left heights. So 17 times 2, 34. My area using a left Riemann sum with 4 subintervals is approximately 34. Now, would we say this is close to the actual area? Nod your heads or shake your heads. Okay, you should be shaking our heads, right? Now, do we think this is going to be under the actual area or over the actual area? Under, right? Because we're missing a lot of stuff here. We're missing here. We're missing here. Okay? Riemann doesn't care. Riemann says, you know what? I asked you to do this. You did this. That's all we want to do. Okay? That's what we got. Good. Yes, you can kind of see that it's under, but whatever. This is what I told you to do. You got it. Don't worry about it. Let's look at the right Riemann sum. Same thing as the left Riemann sum. Rectangles again. Only the height is going to be determined by the function value on the right of the interval. Again, we're going to use 4 subintervals. We're going to go from 0 to 8. So we understand that we have 4 objects, 4 rectangles. We know the width of my rectangle. My delta x is b minus a over n. Again, it's 2. I'm not always going to ask you for 4, but for this first couple examples, I will ask you for 4, except for the last one. I'll give you 8 just for fun. So now let's place down the 1, 2, 3, 4 rectangles. But now the height of the rectangle would be determined by the function value on the right of each of these subintervals. So take the base of one of your rectangles. I'll go back to rectangle number 2. Go all the way to the right. And the height over that rightmost point is the height you are going to use for that rectangle. This is the height for rectangle number 2. Happens to be at the bottom of my interval. It's not always going to be the lowest point of my interval. It's just going to be whatever's on the right. If I look at rectangle number 3, I go all the way to the right and go up. This is a tall height that I'll be using. Okay? Do your other 2 rectangles. Then go ahead and also understand the function values and the heights, and we can go ahead and calculate the approximate area using a right Riemann sum with 4 intervals. Nine plus 7 is 16, plus 7.5 is 23.5. 23.5 times 2 is 47. Okay, that is my area approximation using a right Riemann sum using 4 subintervals. Does this appear to be over or under the actual? Seems to be over. Does it appear to be closer to or further away from the actual compared to the left? Yeah, maybe a little bit closer, right? Riemann doesn't care, okay? He actually says, you know what? Right Riemann sums, left Riemann sums, equally as powerful. They're fine. They're great. It's all about what I ask you to do. Moving on. Midpoint Riemann sum. Same deal. Rectangles. Only you're going to use the heights over the middle of your interval. So, 4 subintervals. We've done it before. The width is 2. I'm going to use green here. 0 to 2, 2 to 4, 4 to 6, 6 to 8. But go to your base. Go over the middle of your base. The function value over the middle of your base is the function value you will be using. So for my 4th subinterval, I'm going over the function value in the middle. I'm going to be using that value. Okay, go ahead and do the calculations. Hurry up though, you don't want to miss the trapezoids. Area, using a midpoint Riemann sum with 4 subintervals is approximately, going up here to my table, I like to list off the bases, circle the heights. We got 4 times 2 plus 4.5 times 2 plus 4.5 times 2 plus 8 times 2. Factor out 2's. 9, 13, 21, 42. Might be pretty close to the actual, right? Don't care. Do not care. Riemann says that left Riemann sum, that midpoint, that right Riemann sum, that midpoint Riemann sum, equally as powerful as one another, as long as you just change one thing about what you're doing. Okay? Let's move on to the trapezoidal Riemann sum. Now we're going to switch our objects. Now, let's remind ourselves about what a trapezoid looks like. Well, you are used to trapezoids looking like this. Okay? Where we have a base 1, a base 2, and a height. Oops. A height. Now, who remembers the area formula for a trapezoid? Yes, exactly. It is 1/2, I'm going to put my height first, times the sum of my bases. 1/2 h b1 plus b2. Now, the trapezoids we're going to be using are not going to look like this. I'm actually going to rotate this on its side, 90 degrees. So what ends up happening, and we're going to flatten out kind of this little triangle here. So it's going to look like this. So it ends up being like a triangle on top of a rectangle. It's a trapezoid. Now when I shift it this way, the height ends up down here. And my B1 ends up over here, and my B2 ends up here. So that B1 and those B2s ends up being kind of like heights, as we know, going up and down. And the height is now like our width going left and right. All right, so now we're going to approximate this area from 0 to 8 using a trapezoidal Riemann sum with 8 subintervals. 8 subintervals. All of a sudden, our width has changed because I'm using 8 objects. The width of each of our objects is 8 minus 0 over 8, which is 1. Okay? So we can go ahead and put down our width. 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. Okay, now I'm going to change up this formula a little bit, right? Because if we're talking about a width, we usually consider it a delta x. Well, if I flip this over, I can see that if I place a line going up to this function value and this function value, and connect the two with a straight line, I've created a trapezoid. Here, let's do my second trapezoid. Lines going up to the heights, connecting with a straight line, we have a trapezoid. Okay, well, let's look at that. What does that appear to be on my, on my graph? This h ends up being a delta x. And this B1, B2 ends up being like a function value F1 and a function value F2. Okay, so we're used to 1/2 h B1 plus B2. It's going to turn into 1/2 delta x F1 plus F2. or fn plus 1. Okay, go ahead and draw the rest of your trapezoids, and then we'll go through the calculations together. Just connect your heights with whatever. Straight lines. Now, you can see, man, this is going to be a pretty good approximation, pretty close to our actual. Riemann doesn't care. Riemann says this one is just as good as midpoint, it's just as good as the left, it's just as good as the right one. The left Riemann sum, that horrible under approximation we got, is just as good as the trapezoidal Riemann sum, provided you just change one thing. Okay, we'll talk about what we'd have to change. But let's go ahead and find this calculation. It's pretty involved in terms of its calculations. Okay, so the area. Well, this first one would be a 1/2. My width is 1. My heights are 1 and 4. It's the two heights from 0 to 1. Plus my second one, 1/2, width is 1, that's the height. F1 plus F2 becomes like F2 plus F3, that's 4 plus 5. I'll do two more, 1/2, 1. Next one is 5 and 4.5. And then we can dot, dot, dot. And the last one, 1/2, 1. That should be a times, not a plus. And the last two heights are 8 and 7.5. Okay? Well, again, I can factor out the 1/2 and the 1. And let's just make our calculations a little easier. Our area is approximately 1/2, 1. Factor that 1/2 of that 1 out. I have 1 plus 4 plus 4 plus 5 plus 5 plus 4.5 plus dot, dot, dot plus 8 plus 7.5. Now, we should notice something. These heights in the middle are used in two trapezoids, right? We got the 4 from the first trapezoid, but then in the second trapezoid, we use the 4 again. We got the 5 twice. We have the 4.5 twice. We'll have this 8 length in both this one and this one. So the 8 is twice. The only ones that occur once are the first height and the last height. We can use that to our advantage. If our widths are consistent, I could actually write this area as 1/2 my consistent widths, first plus my last, plus double all of my middle heights, which I actually can write out. Not too much trouble. 4, 5, 4.5, 4, 4.5, 7, 8. Now, what is that again? If delta x is consistent, your area using a trapezoidal Riemann sum is 1/2 your delta x, your first height plus your last height, plus double the sum of your middle. And this is a kind of a shortcut formula. Might save you some time. Okay? Question?
Approximation get more accurate, more sub-intervals?
We'll get there. Again, trapezoidal, midpoint, right, left, all equally as good. Even though this trapezoid looks great, left one could be just as great. The right one could be just as great. Now, it is important to understand over and under approximations. Now, we're going to focus on left, right, and trapezoidal Riemann sums. Now, in each of these three graphs, f prime is positive. My function is increasing. It's positive with no concavity. It's positive concave up. It's positive concave down. We could actually change concavity. I want you to tell me if a left Riemann sum is over or under the actual for all three situations. Okay? Now I'm going to do the first one. I'm going to just go ahead and just make two intervals just to be able to see things clearly. And I'm going to use the function value on the left of my interval. So that's this one, and that's this one. Well, I can definitely see that my left Riemann sum is going to be under my actual. See if that's the case for an increasing function that is concave up and concave down. Go. Is it also under, or is one of them going to be over? Discuss with your neighbors. Are they over or under? Yeah, turns out the left Riemann sum is under every single time a function is increasing, right? Because think about a left Riemann sum. You're using your leftmost point. Well, a strictly increasing function, the left point will be the smallest value of an interval so long as your function's increasing on your interval. Concavity doesn't change things. No matter if it's concave up or down. What about a right Riemann sum? Well, let's see. Rightmost point, rightmost point. That looks to be over. Is it always going to be over? It's over always. Again, as long as your function's increasing, no matter the concavity, the right Riemann sum is over. Midpoint Riemann sum, too tough to tell. We're not even going to look at it, okay? So don't even bother. Now, we're going to look at a trapezoidal Riemann sum, but the trapezoidal Riemann sum we can see is going to be the exact if you have a straight line. So let's just look at if we have consistent concavity. And if our concavity changes, and here if the concavity changes for the first two, we're still going to be under, we're going to still be over. Trapezoid's tougher. If our concavity changes, we wouldn't know. But see if our trapezoidal sum is going to be over or under for these, and if they're going to be the same like with a left and a right Riemann sum. Because I'm connecting with straight lines, we should be able to tell that the first one is going to be over, and the second one's going to be under. So for a trapezoidal Riemann sum, concavity matters. Concavity matters. Now, for an opposite situation, if I'm decreasing, these two would flip-flop, okay? And actually, these wouldn't, right? Think about a concave up function that is decreasing. Well, if it's a decreasing function, now the left Riemann sum is over, okay? The right Riemann sum is under, okay? So we flip-flop if I'm decreasing. But look at a trapezoidal Riemann sum. Is this going to flip-flop and be an under because we're decreasing? No, still over. So it's like, I don't want you to memorize rules, but what I want you to do is to be able to just see that concavity is very important in determining if trapezoidal Riemann sums are over or under, where it is not important at all when determining if a left Riemann sum or right Riemann sum is over or under. Okay? Got that? Draw your pictures. Don't memorize rules. Cool. Now, back to the whole Riemann saying left and a right and a midpoint and a trapezoid, all powerful. I saw that midpoint Riemann sum, and I said, man, that looks great. This has got to be the one we're going to use in the future. He says, no. They're all equally as good. We should answer this question really quickly. I'll do it really quickly. Sorry. If, this is a question you might see like on a quiz or on a test. Given a function with positive function values and derivatives that are negative, the left Riemann sum over and under. What I would recommend doing is sketching a function that has positive function values, but we know this means we're decreasing. Doesn't matter what the concavity is, a left Riemann sum is over. Okay, so sketch, draw rectangles, it will help you, guaranteed. All right, now back to what I was just going for. Trapezoidal Riemann sum, left, right, midpoint, all equally as powerful. Because if I wanted to do better and get a better approximation with any of them, so that they all are giving me great, great, great approximations, discuss with your neighbors what you think we can do so that each of them produces better and better and better approximations. Go. All right, what do we say? Somebody just shout it out. Yes, make the width smaller, use more shapes, okay? Use more shapes. Well, if we're going to use more shapes, I actually don't want to use the trapezoidal Riemann sum because, man, look at that formula, look at all those calculations. Really, the easiest calculations I had were with these Riemann sums, left, right, or midpoint. So, like, the right's easy enough. Why don't we just use a right Riemann sum? All I need to do is just use more shapes. So this is like, it's about 20 rectangles, okay? So a better approximation is going to be taking a sum of these right heights. I'm going to use f of xi. I'll start with my first height. That's going to be kind of on the right of my interval. I'll go to 20, and I'll multiply by my delta x. Boom. That's going to be a better approximation. Okay, using 20 rectangles. All right. Can I do even better? How many rectangles should I use? Exactly, right? If I use 40, it would be better than 20. If I used 100, it would be better than 40. If I used 1,000, it would be better than that. If I used 2,000, it would be better than that. So, you know, if in general, our approximate area is a sum of heights times widths. Again, this is the height. This is the width. This is just a right Riemann sum with n objects. What are we going to try to make n? What do we want n to be? Infinity, right? Now, I don't like to plug in infinity. Infinity is more of a concept. So I'm not going to just take n and replace it with infinity. What should I use so that I say, hey, take that n and let it approach infinity? A limit. Okay, great. Now, that's going to give me such a great approximation that the more and more and more and more I use, the better and better and better and better and better approximation until we are essentially approaching the exact value, right? And we're approaching a value, we will actually almost like practically get there. We will get to the exact value, okay? So that's how we're going to get the exact area. We now know like a way to write down the exact area using some notation using limits. Limit as n approaches infinity of this sum, starting with 1 going to n, of f of x sub I times delta x. Now mathematicians are like, okay, this is it. This is what we are going to have to do. This is how we're going to have to get the exact area. Now how we do this is a whole separate question. But they're like, we're going to use this concept a lot. We're going to use it so often that we're going to write it down so often that we don't want to rewrite this every single time. That's annoying. It's going to be repetitive. Let's replace this with a different notation. Okay? So they come up with different notation. So instead of, I'm going to write it again just so that you can see it. Instead of exact area being an infinite sum looking like this, I know, Siri, it's exciting. Okay, exact area, it's just an infinite sum. We have an infinite sum. They said replace this with a tall, skinny f that looks like that. Okay? This is replacing this. It stands for an infinite sum, just like the other one does. Okay? Instead of all of this, limit as n approaches infinity of the sum, boom, tall, skinny s. All right, now we got f of x sub I. We'll just put f of x instead. Now let's go back to this delta x. This delta x, what was it? What was the formula for it? Right, b minus a over n. Now, as n approaches infinity, what is happening to delta x? What is happening to the width of our objects if I'm putting infinite amount of objects? It's getting very, very close to 0, right? But it's not going to be 0, because if we're multiplying things by 0, I get 0, but it's going to be infinitely small. So instead of like an overall change in x, instead of this delta x, which is an overall change, we're going to be an instantaneous change. We've used notation for an instantaneous change in x before. What was the notation we used for not an overall change, but an instantaneous change in x? A derivative, or what x? We said tangent slope was instantaneous change in y over instantaneous x, instantaneous change in x. What was the notation we used? Yeah, the D guy. If this is approaching 0, we use dx. That's an instantaneous change in x. A lot of us just use it, but not understand that this can be replaced with that if we know that it's going to be approaching 0. That's its x. Now, the delta x included a b and an a, and actually this xi is going to include a, and it's going to tell us where to start, but we don't have any kind of inclusion of an a and b, so we actually put a and b here. This stands for infinite sum. This is called an integral. Just a small skinny f. It's called an integral. The entire equation here, again, is exact area under a curve. This is red. The integral from a to b of f of x dx. Okay? It's just notation. What does it mean? Area. How are we finding this area? We're taking an infinite sum of very, very skinny rectangles. Okay? What it means? Area. How do we get it? Infinite sum of skinny rectangles. Okay. Now, we're going to skip a little bit. Skip. Go here. Okay? And we can actually write out, the area here shaded in pink using an integral. Okay? You're like, what is that exact value? Well, like finding the exact value, still a tough thing that we're not going to be able to do for another 2 lessons. But we can say, oh, a notation expression for that area is the integral. We're going to go from -2 to 2 of f of x dx. But instead of f of x, you can actually use the function 4 minus x squared. Now, since we're using 4 minus x squared, we're going to replace that with parentheses. It's important to put parentheses around your function before the dx. That way you don't think you're just multiplying the width by x squared. You're multiplying it by 4 minus x squared. That's the height times the width. Okay? Good. That's the easy one. If I did the next one, that's easy. Oh, the previous one, sorry. The previous one. The area under x squared between 1 and 9. Well, I can kind of see what it looks like. I don't know what to do, but I know how to express it using notation. Okay, this area right here between 1 and 9, I would say it's an integral starting from 1 going to 9 of x squared times dx. That's easy enough, right? Since it's not like 4 plus x squared, and it's just x squared, we don't have to necessarily put this x squared around, in parentheses, but good practice too if you do. Well, I could also express it using that limit notation that we just kind of said was equal to. That one's tougher. Let me show you what it looks like. Okay? We know that this is the same as the limit as n approaches infinity of the sum. I starts at 1, goes to n, of f of x sub I times delta x. All right. Now, yeah.
What is the height?
So that is why we're using a right Riemann sum. And instead of starting at 0, we're starting at 1. And I'll show you why by what x sub I is equal to. Okay? So this 1 and 9 is saying start at 1, go to 9, infinite sum, boom, we got it. Okay? But here, we kind of don't have this A and B, this starting point. Like, we know we're going to probably use the first rectangle is going to be like this rectangle to the right of 1. And we're using a right Riemann sum. We're going to use a rectangle there. But like, what is the value we're actually going to use? Well, we know delta x is b minus a over n. I can actually use 1 and 9 to get that this is 8 and over n, where we replace that with b minus a. Okay? Stay with me. You have to know how to do this. This is like more complicated and annoying than anything. Okay? The x sub I is what are the x values that I'm plugging in to use my right Riemann sums? Well, it's a starting point plus a multiple of my delta x. Okay? So if I'm using, 8 subintervals, each width is 1, I would use the first, I'd do 1 times 1 plus a, that is telling me that I'm going to like 2. That's why I'm starting at 1. I starts at 1. Okay, so this turns into a 1 plus I times 8 over n. And I can actually rewrite this whole thing starting by replacing x squared for f of x. So let me show you the first thing I could do. I can rewrite this as a limit as n approaches infinity of the sum r starts at 1 goes to n of xi squared times delta x. Sure. Now comes the part where I will replace x sub I with what it's equivalent to for this situation, and I will replace delta x with what it's equivalent to, and I will have an expression for the exact area under a curve using limit notation. Typically, they'll write 8i over n squared times 8 over n. You probably can tell after doing this why mathematicians would rather write this down here instead of this. They are both equivalent to each other. One is a lot easier to understand conceptually and practically, right? Yeah, not to the end. Thank you. Good catch. This is I times 8 over n. So I just wrote it as 8i over n. Okay? So, again, this guy here is equal to that guy. You could probably see why. Moving forward, we'll pretty much just be using this guy over here. But you're required to know how to write this.
For the AP test or for the test review?
For the AP test. I would not have taught you this if it wasn't on the AP test, because it's just more tedious and annoying. See if we can do it for this guy. Ready? Easy. Start with your formula. Limit as n approaches infinity of the sum. I starts at 1 goes to n of f of x sub I times delta x. No, I can, yeah. I'm just writing. I'm just like saying it fast, but trying to write it. I know, it's crazy, right? You guys can't just write down what I'm saying. Limit as n approaches infinity of the sum of I versus 1 and n of f of x I delta x. You can't write that down. Kidding. I'm kidding. I'll slow down. I'm sorry. Everything's fine. Delta x, b minus a over n. In this case, it's 2 minus negative 2 over n. 4 over n. X sub I. A plus I delta x. Negative 2 plus I times 4 over n. I'll start by using the actual function. Question? A is negative 2, starting at negative 2. That's A. No, so it's B minus A. 2 minus negative 2. Positive 4 over N. You start with B. B minus A. B minus A. Okay, I will replace this with 4 minus x squared, but it'll be 4 minus x sub I squared. Then the final step, plug this in for x sub I, plug this in for delta x. Just notation. The integral being easy, this limit notation being a little more difficult / tricky / annoying. Okay, see if you can do the third one in both ways. Integral, easy, which is why after this unit test, you're never going to see the limit notation again. And then the limit notation. Whoops. That's it. Those are equivalent to each other. You can see why we're going to use the one on the left more often than the one on the right. Okay, just tricky. It's more just kind of like memorizing. A being like, okay, this is the function value you need to start with. But since I'm doing a right Riemann sum, you need to add a multiple of delta x to know what the next height I'm going to use. You know, times 1 times 2 delta x's. That would be the height of my second one. Question? This is A, this is B. Right? A to B. Usually go left to right.
Yeah, but then when you're looking at it like that, you think 5 is it.
we read it, the integral from a to b of f of x dx. We just make sure you have that down. We read this, the integral from a to b. Okay, so a, though it's at the bottom, is where we're starting. Okay? Yep. Yeah, we're always using right Riemann sums here. So we're always going to use that formula there. Other questions? If I use a trapezoidal Riemann sum, that'd be a lot more complicated if I use that summation notation, right? That'd be crazy. Good thing we're not going to do. Okay, now, go back to where we were. If we have straight lines, we can provide exact answers for these integrals. Because we translate this, yes, it stands for infinite sum of skinny rectangles, heights and widths, but we translate this as exact area. Really, it's not under, it's between the x-axis and the function. Well, if I have straight lines, I can use geometry. Okay? Exact area from 0 to 3 under this function, we have a square. No, it's a rectangle. Thought it was a square. Base times height, I can find exact areas. I can find integrals if they're straight lines. Okay, this is stuff that I know how to do because I understand some geometry. Okay, the second one, I can find this. This is something I can do. It's a triangle, right? From 0 to 3. 1/2 base times height, I can do this. This is 3. Now, notice we're not going to 0. This is starting at -3, going to -1. So use some little dashes to help you out. I'm not going all the way to 0. I'm not starting all the way when we have, an x-intercept. I just have this area here. Now, this is one of those trapezoids. It's a triangle on top of a rectangle. Don't calculate the triangle and add the rectangle. It's going to take you too long. And when we do more and more of these problems, doing triangles and rectangles are going to take too long. Instead, think of it as a trapezoid. This is the width. This is B1, this is B2. 1/2 width, base 1 plus base 2. That's going to help you. You'll be able to do those quickly. Now we'll talk about this more in a little bit. But if our curve goes underneath the x-axis, these function values are negative. If I'm taking an infinite sum of negative function values times the width, well, this area, it's a triangle, 1/2 base times height. It's going to be 3, but I'm going to call it -3. Why? Because the function values are negative. And now you might be saying, but Mr. Messner, my geometry teacher always told me that area is always a positive thing. Well, sure. We're just going to consider some of our areas to be negative, and apologies to your geometry teacher, okay? Because it's an infinite sum. It's an accumulation of function values times heights. If the function values are negatives, you technically get negative area, okay? Okay, good. So, I got pink stuff. You should read this as area from 0 to 2. You should read this as area from 2 to 5. You should read this as area from 0 to 7. Okay? That's it. Since we have straight lines, you can calculate these. 0 to 2, trapezoid, 1/2. Width of 2, height of 1 and 4. That's 5. 2 to 5, under the x-axis. Rectangle, width of 3, height of -3. -9. 0 to 7. Well, you can go ahead and guess, and we're going to include a property. We can just add 0 to 2 and 2 to 5 together, and we get -4. Whoa. Make that 5. Sorry. Like 7. Don't know why that was 7. Okay, make that a 5. All right. 0 to 2, 2 to 5. Add them together, you'll get 0 to 5. As long as you make this a 5. Sorry for that being a 7. Now, I still can't answer find the area under a curve. I understand what the notation would be to represent the area under x squared from 1 to 5, but I still don't know how to find the exact value. We're not going to know for a couple days. So again, if we have curves, and if I'm looking for the area under x squared from 1 to 5, this area here, I know that I can represent this area using an integral, but the best I can do right now is to approximate it, because it's a curve and I don't have geometry for curves. Okay? So, how are we going to approximate it? Best thing to do is to create a table. Just like we did when we did the first left, right, and trapezoidal Riemann sums. Best thing to do is probably provide an over and an under. If we want to calculate everything, we can calculate the left Riemann sum or right Riemann sum, trapezoidal Riemann sum, whatever. But let's see what my table would look like. So I'm going from 1 to 5. There's another little pink blob. So might as well, I'm using 4 subintervals. So from 1 to 5, 4 subintervals, width of 1. So I know I'm going to go 1, 2, 3, 4, 5. These are my x values. I know that my function values, which come from x squared, would be 1, 4, 9, 16, 25. Well, our left Riemann sum, 1 to 2, height of 1. 2 to 3, height of 4. 3 to 4, height of 9. 4 to 5, height of 16. Left Riemann sum is going to be 1 times 1 plus 4 plus 9 plus 16. That is 25, 26, 27, 28, 29, 30. Our right Riemann sum, I'll use heights of 4, 9, 16, and 25. +9, 25. 25 plus 25, 50. 50 plus 4, 54. I know that this is an increasing function, so I know this left Riemann sum is under. I know this is an increasing function, so this right Riemann sum is over. I know it's increasing and concave up. Is the trapezoidal Riemann sum that we're about to calculate over or under? Over, right? Connect it with straight lines. Trapezoidal Riemann sum over. Okay, so what would the trapezoidal Riemann sum look like? Let's practice 1/2, the consistent width of 1. First plus last plus double the sum of your middle. And if you have a calculator, you can find that really quickly. If you don't, then do some math. Okay, it's still the best that I can do. I know what the notation would be to represent the exact area, but I still don't know what it is. Mr. Navarro, are you doing the calculation for me? What do you get? 42? That sounds about right. Okay, that's going to be slightly over. Okay, good. Okay, so we know how to represent exact area. We know with straight lines I can find the exact area using geometry. With curves, the best I can do is an approximate. If I'm given a function, create a table, produce the function values, left, right, trapezoid. Let's look into more of these properties of these areas, okay? Again, this is an integral. This entire thing means exact area. If we just look at the integral, remember it's an integral. Don't call it a little s thingy in class. It's an integral, okay? This integral stands for an infinite sum, okay? Altogether, it's the area. It's read integral from a to b. Of f of x dx. And we're talking about an infinite sum of skinny rectangles, height f of x with dx. Now, if a is to the left of b, and my function is above the x-axis, my function values are positive. My dx's I'd also consider positive, so positive times positive, we call my area positive. If I'm under the x-axis, again, we've already talked about this, we're just kind of making sure we understand. My function value is negative, but my dx's are positive, going from a to b, then my area is negative. Dx is the width of a rectangle. It's an infinitely skinny width. It's an instantaneous change in x, right? Infinite sum, height times width. Base times height, really, but dx we'll call base, right? Base times height. Rectangle, this is dx, base. Okay, the function value, that's the height. Okay.
Would that be negative?
Good question. When is dx positive, or when is dx negative? Well, the key is the order matters with a and b. Okay? This is read from A to B. A to B. So you start with A and you finish with B. Watch if I flip it like this. This is read the integral from B to A. If B is to the right of A, I'm going from B to A, this way, to the left. If I'm going to the right, we know that's in a positive xward direction, right? If I'm going from B to A, I'm going to the left. Well, in this situation, yes, my f of x's are still positive, but now my dx's are negative. You're shaking your head. It's just new. The new is always confusing and scary. Because dx is negative and f of x positive, the area is negative. But we're above the x-axis. Yeah, but we're going from right to left. Yep. Yep. I mean, that would still be it, but now it would be then like, it would end up being the opposite way that you'd calculate it. Don't worry about the b minus a over n. The area is negative. I'm going to the left. Dx is negative. F of x is positive. In the next one, the f of x is negative, and I'm still going from right to left. We would say this area is positive. Go with me. This means if I have numbers from A to B, it is actually going to give me the opposite as my area from B to A. Take the opposite of the area from B to A, you get A to B. So if I go from left to right, it is opposite of what I would get from right to left. Order matters. This is the rule that you kind of have to understand, this property. A to B is opposite B to A. Or the other way around. You could say the opposite of A to B gives you B to A. It's out of the way.
Is there like a reason that you would use it for B to A?
There's going to be questions on the AP exam saying B to A. Yeah, but like if I'm actually asking you to find the area under a curve, no, you would go from A to B. So AP exam tries to trick us, right? So we're ready for it. All right. If I ask you from the area, for the area from A to A, so I'm starting at A and I'm ending at A, what do you think this area is? Good. 0. good answer though. You know, it's like it's got to be something like that. Now 0, there's no area. Okay? So the integral from 5 to 5 of x squared, even though x squared is a curve, you can answer this question. This is 0. Okay? If I have a constant times a function, guess what? I can just find the area under the function and multiply it by the constant. You can do that using this example if you'd like to. If I want the area from A to B, and I add the area from B to C, Ms. Fry, what do you think that's equivalent to? Yes, you do. Holy cow. Come on. Watch. If the area is calculated from A to B, that's this right here. And I want to add the area from B to C. So you would write that as what? Great job. You're welcome. Okay? Easy enough to understand these area properties. If I have a function h and it's equivalent to two functions being added or subtracted together, we could just write two integrals and find the area under each individual one and add or subtract those together. If I have a constant, it's going to be easier for me to just show you like a numerical example. If I want to find the area from 1 to 4 under 5, I know visually what y equals 5 looks like. This is y equals 5. It's a straight line, so I can use geometry. From 1 to 4, I get a rectangle's worth of area. Height 5, width of 3. So this is 5 times 4 minus 1, or 15. So if I want to find the area under a constant k, it's the rectangle's worth of area, k times b minus a. If I have a function plus a constant, using the two previous properties, you can write this as the area under the function plus the area under the constant, where the constant area is k times b minus a. The remaining examples are going to be on the video, which you can watch, so that you can help do your homework. I know this is a lot, and I know it's new, but it's going to be okay. Okay, let's do the examples. Once I find my cursor. There it is. Okay. These are problems given to you where you will be given information. This is like known information. The area under this, whatever function this looks like from 0 to 5 is 10. The area from 5 to 7 under this function is 3. And now here we have questions that we will have to answer using our properties. Like, what is the area from 5 to 0? Well, it's just going to be the opposite of the area from 0 to 5. This is negative 10. The area from 7 to 7. I could have just put any random function. That's 0. Let's do another easy one. The area from 0 to 7. Well, that's the area from 0 to 5 plus 5 to 7. That's 13. The area from 5 to 7 of negative 3 times f of x. That's going to be negative 3 times the area from 5 to 7. The area from 5 to 7 is 3. So that's going to be negative 9. Now, to the two harder ones. Area from 0 to 5 of f of x plus 3. Don't say, oh, that's 10. 10 plus 3 is 13. 13 is wrong. Okay? Write this as two different integrals. The area from 0 to 5 of f plus the area from 0 to 5 of 3. 0 to 5 of f is 10. We know the area from 0 to 5 of 3 is 15. So 10 plus 15 should give me 25. Why is the area from 0 to 5 of 3 15? Because of the whole k from a to b part. Now, let's look at this one. The area from 7 to 5 of f of x minus 2. I'm going to first just say, okay, this is the opposite of the area from 5 to 7 of f of x minus 2. Okay? So whatever I get for my answer here, I'm going to take the opposite of it. Okay? Now, I'm going to separate this into two ones, the area from 5 to 7 of f. And then I can either minus or plus and have a negative 2 in there. So I'm just going to go ahead and just minus the area from 5 to 7 of 2. 5 to 7 of f is 3. Minus, this would be 4. So this is negative 1. I'll take the opposite of negative 1, and I get an answer of positive 1. Last one being the toughest one, keeping track of which one goes where and all of your properties. Next one, we have information about f from 2 to 6 and information about g from 2 to 6. Well, what's the integral from 2 to 6 of f plus g? Now, you can just figure out that this is 8 very quickly. But properly, you should probably rewrite it into two different integrals, knowing that you can. From 2 to 6 is 10. 2 to 6 is negative 2. 10 plus negative 2, 8. Now, this one, careful, 6 to 2. Opposite of 2 to 6. I'm going to start out immediately and say, I'm going to find my answer from 2 to 6, and then take the opposite of it. Okay? Now, I'm going to take the opposite of the area from 2 to 6 over g. I'm going to split this up. Minus 2 times the area from 2 to 6 under f. Under g, this is negative 2. Under f, this is 10. So I got 20. Negative 2 minus 20 is negative 22. Take the opposite of it. It's positive 22. Another one. I have information about 0,5 of 3 f of x dx equals 6. 0,5 of g is 7. 3 to 5 of f minus g is 2. Well, immediately going to just rewrite this guy here and say that the integral from 0 to 5 of just f dx is 2. So that area under f from 0 to 5 is 2. So 0 to 5 of f minus g. Well, f is 2 minus g is 7. 2 minus 7. If you rewrote it out, you can figure it out, but you don't have to. This would be proper to rewrite it. Two minus 7, that's negative 5. 0 to 3 of f minus g. All right, So this is tough. I don't have anything about 0 minus 0 to 3. Okay? But what do I have? I have 0 to 5, that's negative 5. I have 3 to 5, that's 2. Well, 0 to 5, 3 to 5. Well, 0 to 3 plus 3 to 5 is 0 to 5. Okay, that's what I'm going to use. The integral from 0 to 3 of f minus g plus the integral from 3 to 5 of f minus g. That equals the integral from 0 to 5 of f minus g. So 0 to 3 is what I'm trying to find. 3 to 5 is 2. 0 to 5 is negative 5. So what does this have to be? Negative 7. To solve. We can do these questions with a graph. So example, integral from 7 to 5 of f of x plus 3. Again, this right to left, keep track of it, pay attention to it. It is the opposite of the integral from 5 to 7 of f of x plus 3. Now, how am I going to find this? Well, I'm going to rewrite this as the opposite of the area from 5 to 7 under f plus the area from 5 to 7 under 3. Under f, area from 5 to 7, this is a rectangle, width 2, height negative 2, this is negative 4. So I'm going to take the opposite of negative 4 plus 3 from 5 to 7. This is a rectangle, height 3, width 2, that's 6. So this is positive 2, make it negative. This ends up being negative 2. Area from 2 to 2. That's simple, it's just 0. Easiest one you can see. Area from 4 to 7 of the absolute value of f of x. Well, if this is f of x, what is the absolute value going to look like? Well, as long as you have positive values, keep them positives. If you have negative values, make them positive. So this would be the absolute value piece that would change right here. This would go up to 7, 2. Okay? Area from 4 to 7, width 1, height of 2. This would be 1. And then from 5 to 7, again, this would be a positive 2. 1/2, 2 times 2. So this would be positive 3. Okay? And that's it. This lesson is going to be up, and I'm also going to keep the 2 separate lessons taught over the course of 2 days up in case you want to focus on one part or the other, whether it's the definite integrals, properties part, and the examples that I just did, or the Riemann sums part, and more focus on that. Okay? Lots of stuff, yes, I know. Thank you for being attentive.